Welcome to Lecture 6.5, Self-adjoint differential operators. In an earlier lecture, we gave examples of orthogonal functions arising from differential equations, or ODEs. We started with Fourier series, which involved sines and cosines, which were orthogonal with respect to a special inner product. Then we saw Legendre polynomials, and then Chebyshev polynomials. However, we didn't give the reason for why these things all happened to work, why they were orthogonal. I think in two of these cases I showed you a differential equation, but I didn't say too much about that. It turns out that the reason why they exist is because they are eigenfunctions of a self-adjoint differential operator. This is an important piece of information that would not have been motivated had I said it at the time, because we didn't know about self-adjoint linear maps and how there's always a basis of orthogonal eigenfunctions. This is the idea of Sturm-Liouville theory, which we will summarize here in this lecture. We will not assume any knowledge about differential equations other than what they are, and I guess what it means for a function to be a solution of one, something that you don't need to take a differential equations class to understand. You often see it in calculus. For those of you who are interested in more detailed information about this, specifically the differential equation aspect of it, I encourage you to check out my series of lectures within my Advanced Engineering Mathematics course. Specifically, I have a lecture on self-adjoint linear operators, which the content of should not be new to you at this point in the class. But then after that, I have 3 lectures, one of them titled Sturm-Liouville theory, then generalized Fourier series, and finally some special orthogonal functions. And in this last lecture, a lot of the examples that I have there are going to be ones that we see in this lecture. But that said, I go over those topics from a little different perspective with different background knowledge and with a different focus. So if this material interests you, and it's my hope that by the end of this lecture it will, I think it's really neat, then I encourage you to check out these lectures. Here's a formal definition, and don't worry too much about the details here. A Sturm-Liouville equation is a second-order ODE of the following form. So it's negative d dx of p of x times y prime plus q of x y equals lambda w of x times y, where p, q, and w are some positive functions. Now, this should not make sense looking at this, why the heck it is defined this way. I will say a little bit more about this shortly, but right now, this should jump out at you as, like, that is strange. It looks very, very specific, but it actually turns out that any second-order differential equation can be written in this form if you set it up the right way. And that's also not obvious, but once again, please check out my series of lectures in my other course if you want to know more. We are usually interested in solutions to this equation on an interval, a to b, under what we call homogeneous boundary conditions. So to motivate the idea of an interval, you either have like a bar of, say, length L, or maybe a guitar string that is being plucked back and forth. So these come up especially when you have like the heat equation or the wave equation. So this looks complicated, this system of equations, but by far the two most common examples are where the endpoints are fixed. I'm going to go with the heat equation at a certain temperature, like 0 degrees at both sides. So maybe it's sitting inside a room that's 0 degrees and the endpoints are uninsulated. And this happens, or if this happens, then we say y of 0 equals 0, and y of L equals 0. And the other case is if instead of these being open, maybe these things are insulated, so heat cannot pass. And so we can write that as y prime of 0, the rate of change of heat through the left end point and the right end point are 0. So these are two very special cases. The first one is where alpha 1 and beta 1 are 1, and alpha 2, beta 2 are 0, and the other one is when these are 0 and these are 1. And now if you want to fix the endpoints to be non-zero, which is often the case, those are inhomogeneous boundary conditions, and there's a whole nother way to deal with that. It's actually, again, I'm going to refer you to my other lecture for details. And there's other ways to do like linear combinations of these, and people study that. those might correspond to some sort of leakage, but I don't really want to get into that. These are by far the most common, but the theory does work for general linear combinations of these alphas and betas. So together, this differential equation and these so-called boundary conditions are called a Sturm-Liouville problem. Let me make a quick remark that I hope will slightly demystify this Sturm-Liouville equation. So consider the following differential operator. L equals 1 over w of x times negative d dx of p of x ddx plus q of x. So this is a differential operator. It's something that you can apply to a function y. You can express this operator as a composition of two operators, L1 and L2. So first of all, take a function y and apply p of x ddx, which sends it to p of x times y prime. And then you apply this L2, which is negative 1 over w ddx plus q over w, and you send this function to this horrible mess right here. So I don't think there's too much to be gained from actually doing this yourself. Just know that this operator breaks up into the product of two of them. And a Sturm-Liouville equation up here is just an eigenvalue equation, Ly equals lambda y. And here's the key fact. Here's the one thing that I want you to take away from this. This mysterious linear operator L is self-adjoint. That's the crux of everything. Let me summarize and clarify what I just said. If we fix an interval AB and boundary conditions given by alpha and beta, as I put on the previous slide, then the Sturm-Liouville operator L happens to be self-adjoint on the vector space of smooth functions on that interval with those boundary conditions. Now, when I say self-adjoint, it's with respect to an inner product. And the inner product of f and g is defined as the integral over that interval, a to b, of f of x times the conjugate of g of x times this weighting function, w of x dx. Now, the details of this, you don't need to memorize this. Just know that, as a consequence, the eigenvalues are all real, and it can be shown that they are unbounded and can be ordered in increasing order, diverging off to infinity, like this. Secondly, each eigenvalue, lambda I, has a unique, that's unique up to scalars, eigenfunction, yi of x. And finally, with respect to this inner product, these eigenfunctions form an orthogonal basis on the subspace of functions that satisfy the boundary conditions. And I say orthogonal because they could be normalized to be orthonormal, but it's usually easier to deal with them unnormalized, say as polynomials with integer coefficients, rather than with some crazy radical coefficients. Here's one more definition. If f is any smooth function on a to b with these boundary conditions, actually it can be piecewise, doesn't even have to be smooth. There are some analysis and convergence details that I will absolutely not talk about there. But anyways, f can be written uniquely using this basis. In other words, as a linear combination of the eigenfunctions. So f of x is the infinite sum of Cn yn of x, where Cn is the projection of f onto yn. And since we don't assume yn is normalized, that's the inner product of f and yn over inner product of yn with yn, where this inner product is defined by this integral. And so it has that expression right here. This is called a generalized Fourier series with respect to this orthogonal basis of eigenfunctions and weighting function w of x. So this is called generalized because the standard example is for a very simple differential equation involving simple harmonic motion where the eigenfunctions are sines and cosines. And we'll start with that one first. The rest of this lecture is just going to be examples, some of these old and some of them new. And I'm not going to spend as much time going over the details, especially the differential equation aspects of this. So once again, if you're interested, please check out my lectures on advanced engineering mathematics. So we'll start with Fourier series. This is a differential equation, negative y double prime equals lambda y. That comes up in a lot of applications. And these boundary conditions that I showed you before, now the length L is equal to pi. It makes the math easier, but it can be adapted to be any number instead of pi. And these conditions where y is 0 at both endpoints are called Dirichlet boundary conditions. Think of it like you have the heat or wave equation on a finite segment, and if it's the heat equation, the temperature is 0 at the left endpoint. If it's the wave equation, the displacement is 0 at the left endpoints, like if you're plugging a guitar string. So this equation here is a Sturm-Liouville problem with eigenvalues n squared for every positive integer and eigenfunctions sine of nx. It's easy to check that every sine of nx, every function like this, satisfies this differential equation where lambda equals n squared. The orthogonality of the eigenvectors guarantees that any two of these, ym and yn, if you take their inner product, in other words, the integral from 0 to pi of ym times yn times the weighting function, which is 1. In other words, the integral from 0 to pi of sine mx times sine nx dx is simply 0 if m and m are different. That's by orthogonality, and you can check that it turns out that it's pi over 2 if they are the same. Note that this means that the norm of yn with respect to this Sturm-Liouville inner product, and that's the square root of the inner product of yn with itself, is the square root of pi over 2. In this case, our generalized Fourier series is just a plain old Fourier series. Any function f of x continuous on 0 to pi that also satisfies these boundary conditions. Now this can be weakened to be piecewise continuous, but again, that's just a bonus. Can be written uniquely as a sum of sine waves, where the coefficients bn are just the projections of f onto the functions sine of nx. So that's the inner product of f with sine of nx over the inner product of sine of nx with itself. In other words, it's the integral from 0 to pi of f of x sine of nx dx over the norm squared of sine of nx, which is 2 over pi times the integral from 0 to pi of f of x sine of nx dx. So this is an example of a Fourier series. Technically, it's called a Fourier sine series. I also have lectures on that, and they are not the ones that I mentioned earlier, so check those out if you want. Our next example is similar, and the only difference is that we have different boundary conditions that are called Neumann. So these correspond to the endpoints being insulated if we are in a heat equation. So this is a Sturm-Liouville problem with eigenvalues n squared. This time we have to include 0. More on that in a second. And the eigenfunctions yn of x are cosine of nx. Notice if n equals 0, then we have a constant solution to this, which we did not get for the previous one because sine of nx is just 0. That's why we had to include a 0 here. The orthogonality of the eigenvectors means, as before, if you take the inner product of any two of these, in this case, that's the integral from 0 to pi of cosine mx cosine nx dx, is also 0 if m and n are different, and it's easy to check that it's pi over 2 if m and n are the same and are bigger than 0. It's slightly different for n equals 0. Once again, this means that the norm of yn, in other words, the square root of the inner product of yn with itself, is root pi over 2 if n is positive. And I didn't say it here, but it's easy to check that this ends up being pi if m and n are equal to 0. So the norm of the constant function 1 is root pi. We also get a Fourier series here. Technically, this is the Fourier cosine series. It says that any function f of x continuous on 0 to pi, or secretly piecewise continuous, that satisfies these boundary conditions, can be written uniquely as a sum of cosine waves. We're starting at 0 because that first one is just a constant. Here, an is the projection of f onto cosine of nx. So here's that formula. It's the integral from 0 to pi of f of x cosine nx dx over the norm of cosine of nx squared. And except when n equals 0, that is 2 over pi times the integral from 0 to pi f of x cosine of nx dx. And you can check that you actually get this same formula if n is equal to 0. I won't do those details here. As I mentioned in the beginning of this lecture, every second-order linear homogeneous differential equation, that is something of the form y double prime plus p of x y prime plus q of x y equals 0, can be written in self-adjoint or Sturm-Liouville form, so like we had in the beginning. I don't think I actually do this in the lecture in my other class, but I think it's a homework assignment, and I kind of guide you through the steps of it. So check that out if you want to know more, or if you want some hints of how to show this. It's actually not that bad. Here are some examples of Sturm-Liouville equations from physics and engineering. The first one should look familiar, Legendre's equation. We saw this in a previous lecture in this class. This is 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 times y equals 0. This is used for modeling spherically symmetric potentials in the theory of Newtonian gravitation and in electricity and magnetism. So when do we have spherical objects? We have them in astronomy, Newtonian gravitation, and we have them, so they're very big and also they're very small. Like if you want to model the wave equation for an electron in a hydrogen atom, that's going to be spherically symmetric. So I actually have a lecture on the wave equation in other coordinate systems in my previous class. I think that's one of the last ones. So if you want to see more about this, I actually think I derived this from a partial differential equation in spherical coordinates. The second one is parametric Bessel's equation, x squared y double prime plus xy prime plus lambda x squared minus nu squared times y equals 0. This is used for analyzing vibrations of a circular drum, so the wave equation in polar coordinates. I also have a lecture on this in my other class. Chebyshev's equation. This is 1 minus x squared y double prime minus xy prime plus n squared y equals 0. This arises in numerical analysis techniques. Hermite's equation, y double prime minus 2xy prime plus 2ny equals 0. This is used for modeling simple harmonic oscillators in quantum mechanics. Legendre's equation, xy double prime plus 1 minus xy prime plus ny equals 0. This arises in a number of equations from quantum mechanics. And finally, Airy's equation, y double prime minus k squared xy equals 0, models the refraction of light. In the remainder of this lecture, I'm going to go over these first 4 applications in about the same level of detail that I did with Fourier sine and cosine series. Let's start with Legendre's differential equation, which, recall, comes up in the wave equation in spherical coordinates under spherical symmetry. So if this is our object, this could be a planet or a sun or an atom, and we are looking, and we want to know the displacement u in terms of the coordinates r, theta, and phi, and the time t. Now, under the assumption of spherical symmetry, u does not depend on theta and phi, only on the radius away, so we can turn this into a two-variable equation, u of the radius and of t. And what happens with a lot of these is such an equation is going to satisfy a complicated PDE, partial differential equation, so some equation involving partial derivatives of u, both in r and t, and then to solve this, you separate variables, so you put all the r's on one side, all the t's on the other side, and you have this complicated PDE, which turns into two ODEs that you have to solve, an ODE in r and an ODE in time. So this is the general idea. You get a differential equation in space and a differential equation in time. Or if you have multiple dimensions, you get maybe a PDE in space. And the ODE in r that comes up is precisely Legendre's differential equation. So once again, check out my video on wave equation in other coordinate systems. I think it's one of the last ones in that entire class for details on this. So this is a Sturm-Liouville problem. Negative dd. So the thing that I wrote in the previous slide, if you rewrite it this way, it is in this form. So negative ddx of 1 minus x squared times ddx of y equals negative lambda y. So p of x is 1 minus x squared. Q of x was another term that was in here. It's equal to 0. Don't worry about it if you don't remember where these things occurred. And w of x, that was this weighting function on the right-hand side that is equal to 1. It can be shown without too much trouble that for every natural number n, that is 0, 1, 2, etc., we have an eigenvalue, lambda n, which is n times n plus 1. And the eigenfunctions solve this equation where if we plug n times n plus 1 back into here and simplify, we get the equation, Legendre's equation that I showed you on the previous slide. For each n, one of the solutions of this equation, which you have to solve using the power series method, and when you do that, one of those power series ends up terminating, becoming a polynomial. That's called a degree n Legendre polynomial. An easy, or I don't want to say easy, a concise way to define it is recursively like this. 1 over 2 to the n times n factorial times the nth derivative of x squared minus 1 to the n. These are orthogonal with respect to the Sturm-Liouville inner product, which in this case, inner product of f and g is the integral on this interval, I had to make sure I said that right, of f of x times g of x dx. So there's nothing here because the weighting function is 1. It can be checked that the inner product of pm and pn, which is, again, the integral of pm times pn from negative 1 to 1, is, well, of course it's 0 if m and n are different, but if they're the same, then it's 2 over 2n plus 1. So we can write that nicely as 2 over 2n plus 1 times delta mn. By orthogonality, every function f that is continuous on this open interval, and we can also do piecewise if we want, can be expressed uniquely using Legendre polynomials. That is, f of x is the infinite sum of cn pn of x, where these are polynomials, and cn is just the projection of f onto the nth Legendre polynomial. That is the inner product of f with pn over the inner product of pn with itself. And if you take this thing and plug it into the bottom, and you simplify it, I won't do the details, but this is just n plus 1/2 times the inner product of f and pn, where this thing here, of course, is this integral. So this is what I mean where I'm giving you the summary, the sort of high-level basic idea without doing all of the nitty-gritty details. For example, solving this equation is a feat in itself. That's something that I've done things like this, and I think it may take 20 minutes to go through this example in all its details. Just for fun, I think this is a picture I showed you before. Here are the first 8 Legendre polynomials, and here are their graphs. So before I talked about that they happen to be orthogonal with respect to that magical inner product, and now we know it's not quite so magical. It comes up because we are in an inner product space, and they are eigenfunctions of a self-adjoint linear operator. Our second example is the parametric Bessel differential equation, and this is defined on the interval 0 to a. So this represents vibrations of a circular drum, so that is the wave equation in polar coordinates. So it makes sense that the variable is going to be defined on 0 up to the radius of the drum a. So this is negative d dx of xy prime minus nu squared over x times y equals lambda xy. In standard Sturm-Liouville form, p of x is the function x, q of x is negative nu squared over x, and the weighting function w of x equals x. For a fixed nu, which depends on the physical property of the system, so whether it's think of it like how tightly the canvas is stretched, there's an eigenvalue lambda n for every natural number n starting at 1. So this eigenvalue is alpha n squared over a squared. So a is like the radius of the drum. And sometimes we call that omega n squared. You can think of this as the frequency squared. And alpha n turns out is the nth positive root of the function j nu of x, which is the Bessel function of the first kind of order nu. So one way to think about this, I don't know how great this explanation is going to be, but if you pluck a guitar string, it's going to make a note, and you know that those notes are made of harmonics. So it's going to vibrate like this. There's going to be a whole vibration. There's going to be half vibrations. There's going to be third vibrations, and for every integer, there's n. There's going to be, these are called harmonics. So it's similar if you have a vibrating drum. I don't know how I'm going to be able to draw this, but let's take a cross section of that, or let's take a side view of that, like this. You are also going to so you are going to have vibrations that look like this. You're going to have vibrations that look like this. You're going to have vibrations that look like that, and so forth. And of course, you have to sort of revolve this around that center axis to get those actual functions. So these are the eigenfunctions. It's like the two-dimensional polar version of these harmonics. The eigenfunctions, or at least as a function of the radius, notice that they don't depend on theta due to circular symmetry, solve the parametric Bessel's equation, which is x squared y double prime plus xy prime plus lambda x squared minus nu squared times y equals 0. That's the equation that I showed you a couple slides ago on that summary list. If you fix nu, then for each n, there is a solution j nu n of x, which is this Bessel function, j nu of lambda n x. So think of this as like the analog of if sine of x solves y double prime equals negative lambda y, then you also have solutions of the form sine of 2x, sine of 3x, sine of 4x. These numbers, this omega is the frequency, and this omega n, you can think of this as the analog of frequency in this setting as well. These are orthogonal because the Sturm-Liouville operator is self-adjoint with respect to the inner product, defined as follows. The inner product of f and g is the integral from 0 to a of f of x, g of x, x dx. And that x is the weighting function x here. And as I said before, this x is usually the radius. And so you know from vector calculus that you have this rd theta if you were in polar coordinates, and that's kind of what this is here. So this is that extra radius term. As I said before, we get orthogonality by free, but we can also check that the inner product of two of these Bessel functions, which is the integral from 0 to a of j nu of omega nx times j nu of omega mx x dx. It's not a fun integral to compute, trust me, is 0 if n and m are different. And I don't know of a nice form for what this is if n and m are the same. Maybe there is one, but it involves the nth positive root of this, so it's probably not too nice. But that doesn't really matter. By orthogonality, every continuous function, f of x, on the interval 0 to a can be expressed in a so-called Fourier-Bessel series. That is an infinite sum of linear combinations, a cn j nu of omega nx. Now I am using this little tilde symbol instead of equals because there's some details about convergence and what norm or what inner product space it converges in, which isn't because of this weighting function. I won't say any more than that. This is a functional analysis detail. But Cn is the projection of f onto the Bessel function j nu n. So it's the inner product of f with j nu n, which can be expressed with this integral, divided by, actually, this integral itself, the inner product of j nu n with j nu n. Just for fun, here is a power series representation of the Bessel functions of the first kind, and here's a graph of the first 6 of these things. Our next example is Chebyshev's differential equation, defined on the interval -1 to 1. This is negative ddx of root 1 minus x squared ddxy equals lambda times 1 over root 1 minus x squared y. So p of x, in this case, is root 1 minus x squared, this function. Q of x is 0, and the weighting function w of x is 1 over root 1 minus x squared. That's this thing here. For each natural number, there's an eigenvalue, lambda n equals n squared. And so if you plug that back in for lambda and you simplify this, you get Chebyshev's equation, which is what I showed you a couple slides ago. 1 minus x squared times y double prime minus x y prime plus n squared y equals 0. So the eigenfunctions solve this ODE. This is a second order homogeneous differential equation. So the solution space is two-dimensional, and you can solve it using the power series method. You basically assume that there's a solution that is a power series, plug it back in and solve for the coefficients, and you'll get a recurrence relation. It turns out that one of those two solutions ends up being a polynomial. In other words, the coefficients are eventually 0. So for each n, you get a degree n solution. That's called a Chebyshev polynomial, and that is defined recursively as follows. So the 0th degree one is 1. The first degree one, t1 of x, is x. And then the n plus first degree one, tn plus 1 of x, is 2x tn of x minus tn minus 1 of x. These are, by construction, being eigenfunctions of a self-adjoint differential operator, orthogonal with respect to the inner product, which is defined as follows. The inner product of f and g is the integral on this interval of f of x, g of x, divided by root 1 minus x squared, because we're multiplying by the weighting function, w, dx. It can be checked, it's a little bit messy, that if you take the inner product of tm with tn, so that is just this integral here, there are two cases. First, if m and n are equal to 0, this integral, it's actually pretty easy because you just get 1 for both of these, is equal to pi. And if m and n are bigger than 0 and the same, then you get 1/2 pi. Obviously, if they're different, you get 0, and that's given by this Kronecker delta function. By orthogonality, every function, f of x, continuous on this interval. Now, you got to worry about the endpoints because this weighting function is not defined on the endpoints. That's a detail we don't need to get into. But this can be expressed using Chebyshev polynomials. Once again, I will use this convergent symbol instead of equals due to functional analysis technicalities that I will not get into. So f of x converges to the infinite sum of Cn times Tn of x, where Cn is just the projection of f onto the nth Chebyshev polynomial. So that's the inner product of f with Tn divided by the inner product of Tn with itself. And this, if n is bigger than 0, that's 2 over pi because of this, times the inner product of f with Tn. And once again, I'm not going to write down a formula for this. You have it right up here. You just have to put f in for Tn. And it's easy to modify this if n equals 0. Just get rid of this 2 because of this 1/2 versus 1 right here. I showed you this picture in a previous lecture. Here are the first 7 Chebyshev polynomials of the first kind. There are also Chebyshev polynomials of the second kind. I encourage you to look into that if you are curious. And here is a graph of them defined on the interval -1 to 1. Finally, our last example is Hermite's differential equation. Recall that this comes up in quantum mechanics. And this is a Sturm-Liouville problem actually on an unbounded interval, so the entire real line. And this is negative d dx of e to the negative x squared, d dx of y equals lambda e to the minus x squared y. So here p of x is e to the negative x squared, q of x is 0, and the weighting function is e to the negative x squared. It can be checked that the eigenvalues of this equation are 2n for natural numbers n starting at 1, and the corresponding eigenfunctions solve this equation when you plug 2n in for here, which reduces down to Hermite's differential equation, y double prime minus 2x y prime plus 2ny equals 0. Now this might be a bit of a surprise because this doesn't actually have an exponential in it, so those things end up canceling out. And I don't know too much about this because this comes from quantum mechanics. I know that this e to the minus x squared is this Gaussian, and quantum mechanics involves distributions of electrons, and so these things do come up. Again, I don't know the details, so I encourage you to look into it if you want to know more. I do have a lecture on Schrodinger's equation in my advanced engineering class, but I do not talk about Hermite's equation in that. If you solve this differential equation using the power series method, you get 2 linearly independent solutions that are power series, and for one of those things, for a fixed n, it reduces down to a polynomial called the degree n Hermite polynomial. And that is defined recursively as follows. Hn of x is -1 to the n e to the x squared times the nth derivative of e to the minus x squared. And that, curiously, reduces down to the nth power of the differential operator 2x minus d dx applied to the constant function 1. Yes, I find this surprising as well. As I said, I don't really know much about Hermite's equations or Hermite polynomials. I think I just found this out by Googling some of the basics, probably with Wikipedia or Wolfram Math. By Sturm-Liouville theory, these eigenfunctions are orthogonal with respect to the inner product defined as the integral over the whole real line of f of x times g of x times the weighting function e to the minus x squared dx. It can be checked that the inner product of hm and hn, well, we know we get 0 if m and n are different. So that's this integral, hm times hn times e to the minus x squared dx, is the square root of pi times 2 to the n times n factorial times the Kronecker delta and m. So in other words, this is 0 if m and n are different. Otherwise, it's equal to root pi 2 to the n times n squared. By orthogonality, every function f of x in the correct Hilbert space, and when I say correct, there's a lot of details here. the integral over the whole real line of the square of f times e to the minus x squared has to be finite. So this function has to have some sort of finite norm. Such a function can be expressed using Hermite polynomials. In other words, f of x converges to, think of it as equals to the infinite sum of Cn Hn of x, where Cn is just the projection of f onto the degree n Hermite polynomial. So that's the inner product of f with Hn divided by the norm squared of Hn, which is this thing here, root pi 2 to the n times n factorial. Here are the first 8 Hermite polynomials, and here's their graph, or at least part of their graph. So notice how these functions are not going to go to 0. I guess it's not obvious, but these functions do not necessarily go to 0 as x goes to infinity. So you may be worried about the fact that, well, those functions aren't going to have a finite integral over the real line. But don't forget that the inner product of f and g isn't just the standard inner product. It's f of x times g of x times e to the minus x squared dx. So this has a big effect of functions that look like they point-wise aren't going to go to 0 at infinity. They are going to converge with respect to this inner product or with the corresponding norm. So again, these are functional analysis details that I will not get into, and this has to do with why I said f of x, an arbitrary function, is not equal to the linear combination, because that's something that an analyst would probably pick at, but instead it converges to this, and I will very conveniently and happily not provide the technical analytical details. Just for fun, there are some so-called Hermite functions that can be defined from the Hermite polynomials as follows. So these are denoted sine of x, and they are 2 to the n factorial root pi all to the minus 1/2 times e to the minus x squared over 2 times hn of x. So this looks complicated, but remember that the square root of this term here is just the norm of hn of x. So this whole thing is really just e to the minus x squared over 2 times the normalized Hermite polynomial with respect to that special Sturm-Liouville norm. Another way to write this is negative 1 to the n divided by the norm of hn times e to the minus x squared over 2 times the nth derivative of e to the minus x squared. These functions end up being orthogonal with respect to a different inner product, defined as the integral over the real line of f of x, g of x, dx. So it basically gets rid of this weighting function. Every real valued function f that is square integrable on the real line can be expressed uniquely, again that's in quotes because I'm using this convergence notation, as a linear combination of these Hermite functions, where Cn is the inner product of f with psi n using this inner product, which is just the integral of f with psi n of x dx. These are solutions to the time-independent Schrödinger equation, which is negative y double prime plus x squared y equals 2n plus 1 times y. And here's a picture as to what the first few of these Hermite functions look like. So in my previous class, as I said, I have a lecture on Schrödinger's PDE, and I do solve that, but I do not talk about Hermite functions. Okay, that is a good place to stop. I really enjoy seeing how the theory that we built up with inner product spaces and self-adjoint linear operators has such direct and powerful applications in differential equations that model real-world phenomena in the sciences. And I hope you were impressed as well. See you next time.